talk about testing and learning distributions under local information constraints.
Thank you. Thank you for inviting me. And so yeah, I'm going to talk about basically testing and learning discrete distributions under some local information constraints. This is based on a sequence of works with Jaydev Acharya, Cody Freytag, and Himanshu Tyagi. I'm going to mention which ones. So I'm going to start with a lie. Something happened yesterday, but I'm going to pretend it's today. I don't know who of you followed that, but basically we sent something to Mars, which was pretty impressive. That something was essentially a glorified thermometer, which doesn't make it less impressive. By the way, I didn't draw that. That's from the oatmeal. So the main question is why?
I didn't give you a chance to read it.
Oh. So yeah, we sent, I didn't, but NASA sent something to Mars, which is going to measure the temperature of Mars and send us back the results. And from that, scientists will be able to infer supposedly a lot of interesting things. So why am I telling you that, besides the sheer interest of the fact? Well, we essentially sent something there and we expect data back. Now, there is one thing in particular interesting about this setting. It's pretty far, and it's pretty hard to get data back. We've got a lot of very stringent communication constraints on things coming back. For obvious reasons, we've got a lot of noise. We also have the fact that, you have energy, battery constraints. You can't emit too strong a signal. You also have a limited window of communication. For example, when there is a giant celestial body in front of your target, it's pretty useless to send something. You've got to wait until it's gone. For example, the sun, I guess. You can't have too big of a transmitter size. We don't get to send a giant thing there, so you've got to miniaturize and be pretty specific and savvy about what you send. So this is actually a good example of also, you've got the cost of deployment. I don't know the numbers, but we can't afford to do that every time, besides the sheer fact that it takes a lot, like several months to get there. So we would like to have good protocols for that kind of tasks. How do we minimize the costs of sending that, also the risk of failure, etc., accounting for such constraints that we have to take into account. How many sensors can we put on that thing? And how many of those things are we able to send? How do we send information? How do we quantize it? How do we send it? Which kind of protocols is the most reliable, etc. So all that is basically falling under the general overarching goal of how to make machine learning work under some constraints with limited resources. And of course, I'm not going to answer that, but I'm going to try and tackle the more specific question. How do we perform statistical inference under some local information constraints? So the particular by the way, if you've got questions, don't hesitate to interrupt me. So the setting I'm going to consider is called the SMP, the Simultaneous Communication Protocol Model, message passing. It's also known as the referee model. And what we've got is some pre-specified inference task that we want to solve over discrete distributions that are on a known domain of size k. Also, there's going to be colors just to keep track of the parameters. I don't know if that helps, but I kind of like them. We also have, of course, that unknown distribution p underlying the question. We don't know what it is. We just know it's over that domain. And, we've got that referee somewhere that wants to solve the task on that unknown distribution. Now, how do we access that distribution? Well, we've got a bunch of parties, players. Let's call that n. It's red. And each of them, as I said, has constraints. These constraints are going to be modeled by a family of channels that I'm going to call curly W. And each player, the protocol defines how they pick some particular channel. So a channel is just a randomized function that takes an input and outputs something, the message.
So you can think of it as a random variable?
Yeah. W, if I give you input x, W of x is going to be the variable. I'm actually going to use WY condition on X for the probability to output message Y when you give it X. It doesn't need to be the same for all the players. It just needs that specified by the protocol. And each of these n players independently gets one sample from that distribution, performs one measurement, and then sends the message to the referee. And receiving these n messages in a one-shot fashion, hence the name simultaneous, the referee has to solve the task. So now the main question is, based on all the parameters we've got, so blue K, green W, and all the parameters of the task, how many players do we need to perform the task? What's the minimum number n that works? A bit more graphically, this is essentially what happens. So here n is equal to 5 because I can't draw more. But so we've got these 5 parties. Each of them picked a channel, so W1 to W5. And for example, the second one got input drawn from the distribution 271. That goes through the randomized channel and sends 18 to the referee, etc. And the referee reads the 5 tuple 2, 18, 11, 3, 21, performs some computation in a centralized fashion, and says, okay, that was a testing task, says, I accept that the distribution satisfies the null hypothesis. So, some remarks about that. First of all, as I said, W encodes the local constraint. So in particular, if you've got the identity in there, well, there is no constraint. You go back to what I'm going to call the centralized case, which is the referee gets all the samples. Now, I've got that curly P for the task. What is an inference task? It could be density estimation. It could be parameter estimation, functional estimation, like you want to estimate the entropy of that distribution. Or it could be hypothesis testing or distribution testing, property testing. I'm going to focus mostly on density estimation, learning, and property testing. But you should keep all those in mind. Yeah. Oh, sorry.
So can you back up a second? I'm a little confused. Well, is the channel like one dimension of a k-dimensional distribution? Is that, or is it?
The channel is just some function that.
What a channel is.
So the channel is just a function from 1 to k, which is the domain, to some set of messages, so 0, 1 to the number of bits you send. And when you get your sample from the distribution, say you get that number between 1 and k, the channel just is a randomized function that's going to tell you which message to output.
Is it possible you can give an example? I'm a little...
Identity, for example, would be I map 1 to k to 1 to k. It's deterministic. If I receive sample 17, I'm sending 17. It could be also like in 0, 1 saying like, is it even or odd? Or it could be a completely useless channel that just outputs a random bit. That's the kind of, these are possibilities.
So the players have no control over the channels, right?
The protocol specifies which channel each player has.
And are there multiple rounds?
No, it's in the SMP, simultaneous message passing thing, so it's a one-shot thing. Each person gets independently one sample. They pass it through their respective channels, and they send the messages, and then the referee reads that and just.
Sorry, another question. Oh, go ahead. So you were saying that you wanted to estimate some property of the distribution. So when you say identity is trivial, you're only still getting a sample from that distribution. So what does it mean to say n? What is n there?
Oh, each player, you've got n players, each of them gets a sample. So if they can just send their sample, the referee gets n samples from the distribution. So then, for example, if you want to estimate the entropy of the distribution, you just need n to be k over log k. And
I see that. Okay, that's what you mean. Okay.
Is it crucial that the channels are just based on one point, or it could be that one of those get a collection of points and there is a function of this collection?
So all I'm going to talk about only deals with one sample per person. The techniques, in particular the low bounds, I'm going to talk about completely break for more. There's been some work on it on different models where, for example, each person could get more samples and the communication constraint is maybe different, etc. So Ilias has a work on such a model for learning, NIPS 2017, I think. But yeah, I'm going to focus on the case one sample per person.
What are the things that referee is aware of?
The referee knows the protocol, basically. The only thing the referee doesn't know is essentially, the samples. So the referee knows which protocol the players are going to use, knows the number of players, and of course knows the task he or she is trying to solve. One particular thing I'm going to focus on is you also have different available resources. So for example, it might be the case that all the players must be deterministic. I'm not going to focus too much on that. It could be the case that they use their own private randomness. Or it could be the case that actually they also can share some randomness. Think of, for example, the referee gets to broadcast a random string at first. It's easier to hear than to send, so each party can hear the random string, or it's specified by the protocol, and they share some randomness. So that would be public coin protocols. And private coins is when they actually can only use their own private randomness, as is the case in communication complexity, the standard model. Okay. So I mentioned a few tasks before. I'm going to focus on two very specific, I dare say, fundamental ones. The first one I'm going to call distribution learning. And the goal is, given the messages received by the referee has to output some estimator p hat of the unknown distribution. And with high probability, I'm going to fix it to be a constant. It's not that important, but with high constant probability, that p hat needs to be close in some parameter of the task, epsilon, to the true distribution. And that's going to be in total variation / statistical, or equivalently L1 distance. So that's the first one. The second one is a testing task. And that's goodness of fit without loss of generality, uniformity. So the referee just needs to decide whether that unknown distribution P is the uniform distribution on the domain, or is far, epsilon far in, again, L1 distance from the uniform. So it's a composite hypothesis testing question. And again, you need to be correct with high constant probability. And when I say these are fundamental, so it's known that if you can do uniformity testing, you can do goodness of fit, or it's also called identity testing, against any distribution you might know. So that's why it's sufficient to focus on that. So before I talk about what can and cannot you do with information constraints, what is known if you don't have those? So it's folklore by now that if you want to learn a k-area distribution to do L1 distance epsilon without any constraint, you need information theoretically, and it's sufficient to have k over epsilon square samples. It's also known, it's a little bit less folklore, the actual type dependence in these parameters dates from 2008, that if you want to test whether a distribution is uniform or epsilon far from it, you need square root k over epsilon square samples. That's the second one. The dependence on epsilon is due to Paninski. So now that's the baseline. And what happens when you throw in actual information constraints in that? So another question that I'm going to focus on is, then do those public randomness help if they actually can share some public random string, the players, beforehand? So, of course, we're not the first ones to consider these kind of questions. There is a huge body of work with different kinds of constraints. The main two I'm going to talk about are communication constraints. Each player can only send at most L bits, or local differential privacy. I'm going to get back to that. But essentially, you've got, over the past years and even decades, a lot of work in either similar models with similar or slightly different focuses, or in different areas and models. So the plan for the talk, first I'm going to talk about what I'm going to call the communication start setting, which is when each player can only send L bits. The second I'm going to talk about another kind of constraint, which is each player wants to preserve their own privacy, in a formal sense. And after that, I'm going to go to a general lower bound framework that encompasses the first two settings. And then there's going to be a hidden section, which is just the conclusion.
So backing up to that slide where you said when there is no local constraint,
Yeah.
but public randomness is allowed. What was the answer to that question?
So if there is no constraint, there is no public randomness anywhere, right? The referee directly has the samples, so
it doesn't help to
it
have
doesn't. I mean, yeah, it doesn't help. The referee just observes the samples to begin with. Sickly, I can't pronounce his name, but for simple hypothesis testing, it was shown that public randomness doesn't help in that 93 paper. So the first one is the communication start setting. It's a work with Jaidev and Himanshu. And I'm going to start with another story. I don't know who of you is familiar with Boaty McBoatface. If you're not, I'm not going to go through that, but you should definitely Google it. It's worth it. But let's say you're a little bit concerned about, let's say, the temperature of the world, and you want to send a fleet of observation ships, to measure the temperature of the Southern Ocean, to check whether it actually matches the temperature on record. So there is a small issue, of course. All these ships will send back their measurements, and the Southern Ocean is a little bit not nice in the sense of you've got storms, you've got harsh conditions, and you don't have a Starbucks nearby to connect to the free Wi-Fi, so you actually have true communication constraints there. You can't send that many bits reliably. So what is the best protocol in terms of ship efficient, because these things are expensive to build, to man, and to send, in order to test reliably whether the distribution of temperatures matches the one on record. So that's actually a case of goodness of fit here. And with another slide of notation, how does that fit in the previous thing? Well, my family of channels is going to be all the randomized functions that map the domain 1 to k to L bits. I can only send L bits. And I'm going to focus on the case where L is strictly less than log k, because otherwise, well, you have the identity in there. And so with a picture, that's what it is. Each of the boats will send their output to a central referee. And first, I would like to claim there is OneParty approach that, if possible, would give an upper bound for all of that. In particular, if there was a way, given some number of ships/parties, to generate one sample truly distributed according to the unknown distribution at the referee, then you could do anything you can do in the centralized model with some overhead. If it takes T ships to generate one sample truly distributed according to P, then to solve something that requires 1,000 samples, you just send 1,000 T ships. And you retrieve all that at the referee, and then you have 1,000 samples. So it would be nice to know if it's actually possible. Can the referee do that with some number of players? And the first answer we give is no, you can't, which is a bit of a downer. But essentially, even if you can send log k minus 1 bits, you can't simulate with any finite number of players a sample truly distributed according to P. And the proof is not that complicated. It's some suitable version of the pigeonhole principle, essentially. So that leaves us there. We also give another result that essentially says that, yes, we can do that. If we relax the requirement a little bit. So instead of saying I want to generate given T players one sample, I can generate one sample if I've got on expectation some number of players. So more like a Las Vegas, I guess, algorithm. So k over 2 to the L players are sufficient to in expectation to generate one sample. And so before I discuss the implications, some flavor of how that goes for the case where L is equal to 1. I take 2k players, and I pair them. So player 1 and 2 are going to be focusing on element 1 of the domain. Player 3 and 4 on element 2, etc. And player 2i minus 1 and 2i are focusing on element I. And the bit they're going to send is just 1 if their sample is equal to I, or 0 otherwise. And then the referee receives these 2k messages and just outputs I, if two things happen. First of all, the player 2i minus 1 is the only odd numbered player that is sending 1. And on top of that, player 2i sends 0. So that sounds a little bit strange. If you look at it, it's not hard to show that, well, either the referee doesn't output anything because nobody, none of these conditions is satisfied for any I, or if the referee outputs something, it's going to be distributed with the right probability. Also, the probability to not output anything can be upper bounded by some quantity that only depends on the 2 norm of the distribution. And then we want to bound that away from 1 in order to be able to say on expectation, if you repeat that enough times, it works. And when I say when you repeat, you actually repeat it in parallel because you only have 1 round. And there are some tricks that you can use to bound that away from 1, and then you get actually the statement. So, okay, we can simulate samples from the distribution truly from, yeah?
So, sorry, for this strategy that you said that you want to simulate, does it matter if you simulate from a distribution which is close but may not be consistent across all?
So that's the issue. Maybe for some applications it would, but if you want to give truly a universal upper bound, that's not going to be good, right? Because depending on the task, maybe it's going to be actually very sensitive to how close you are to the distribution. So then you would have to go to a much more fine grain, saying like, if I want approximation, like something that is distributed close enough, etc.
Is there an example, for example, where close is not good?
Well, yeah, I mean,
if you can test.
Let's say 1 point, is it in the support or not?
Yeah.
You pick a point and ask, is it in the support of the distribution or not? So being close will not vary.
Basically, anything that's not Lipschitz with regard to total variation distance is gonna be bad. And they might not be always the most interesting properties, but they exist.
So when you say that you have 1 round, you're doing everything in parallel, what does it mean to have an expected number of players?
That per se, just if I had at my disposition an infinite number of players, I would only need on expectation to look at that many of them.
So the parallel is repeating the block of players many, many times.
Yeah. I've got that infinite sequence of players. They all are already, they all send me a message, but I only actually look at some of them. I'm not going to use that by itself. I'm going to use it as a building block. So yeah, just to bounce on that, how do we use that as a building block? Here's the corollary. If I know how to perform some task with sample complexity S in the centralized model, then now I can do that with S times k over 2 to the L players, and then with probability of failure, that's going to be a constant. And the idea is just basically Markov's inequality. I only look at that many players, and if I don't get enough samples, then I say abort. And as corollaries of the corollaries, well, learning a distribution was k over epsilon square. Well, now it's k square over 2 to the L epsilon square. And well, if I want to test, it was square root k over epsilon square. Now it's k to the 3/2 over 2 to the epsilon square. And these, since I wrote private coin, it's actually deterministic because the way to simulate is deterministic. So that's good. We've got some upper bound on these 2 tasks. Now, of course, also the simulation thing I mentioned is also optimal, but the proof is a little bit contrived. We can prove that this is optimal, and so if you could simulate in a better fashion, you would break the lower bound. Okay, so we've got this. Now the question is it really all you can do? Is there anything better than that you can do? And I mean, given the whole thing about private and public coin, it should be kind of obvious that the answer is no, there is something better. So now, if you allow the players to share some randomness, of course independent of the inputs, but share some randomness, then you can do better for the testing case. And in particular, I claim there is a public coin protocol for testing uniformity over domain size k, with L bits per player. So again, think of L as, I don't know, constant or slow growing function of k, where now you only need k over 2 to the L over 2 epsilon square players. So you save essentially a square root k over 2 to the L, square root k over 2 to the L. And So I'm going to give the idea of the proof. Oops. So we're going to rely on that lemma that I'm going to call minimally contracting hashing, because it's a kind of hashing, and the minimally contracting will hopefully make sense at the end of the talk. But essentially, what happens is the claim is just if you partition uniformly at random the domain K into parts of equal size L, in L parts, sorry, of size K over L, and you look at what the original distribution gives as an induced distribution over these L points, then the distance is going to be preserved with constant probability up to some contraction factor that's going to be square root big L over K. Also, if you were uniform, needless to say, you're still uniform because every part has the same size. So that preserves uniformity, and also that the distance to uniformity is shrunk, but not by too much, by that factor. And the proof is not too complicated. Essentially, it's, well, you want to deal with this, but you have dependencies because you take a uniformly random balanced partition. But if you use a standard anti-concentration inequality plus bounding the second and fourth moment, you will actually get this statement. And also, all the parameters up to constants are tight. If you just take the distribution that's very close to uniform, but 1 plus minus epsilon times uniform on each point, this is essentially what you will get. Because on any part, things will cancel out pretty much up to the standard deviation. So that's the lemma we're going to use twice in that talk if I've got time. How do we apply it? Well, big L is going to be 2 to the little l. The players have public coins. They share randomness, so they can definitely pick a uniformly random partition altogether, the same. With constant probability, they're going to be lucky. It's one that preserves the distance up to that factor. And now they just can send the samples on that induced distribution over 2 to the L points to the referee, because they've got L bits. And the referee will just test uniformity with these new parameters. So the new domain size is big L, and the new distance parameter is epsilon prime, which is epsilon times that contraction factor. And things actually work out if you use the standard, like the centralized algorithm. So that's good. Now that was only with constant probability. What do you do? Well, you take a constantly many times more players, and you've got bunches of people doing that. And since uniformity is always uniform, you can actually amplify that to probability 2/3. And the interpretation is you use public randomness to essentially randomly map the domain to a smaller domain, but one that provides the best trade-off between the information constraints you have, the domain reduction, and also the distance shrinkage in chi-square distance. So it was kind of hidden because I didn't phrase the lemma like that, but it's actually what's preserved is the L2 distance. And actually, since I'm dealing with uniformity testing, L2 distance and chi-square distance are equivalent. But under the hood, that's essentially what's happening here. And well, it's a simple algorithm. As we'll see that contraction thing again, it's very general. The only drawback is you use a lot of bits to pick up a lot of common randomness to pick up that partition. But since the analysis only looks at second and fourth moment, actually all you need in there is going to be 4 wise independence. So you can use something a little bit more efficient. And we'll see that contraction again. If that line is a bit mysterious, just wait a little bit. But this is what we get. I rewrote it in a way which is, this is the centralized complexity times the blow-up factor. So for private coin, learning private public doesn't help. For testing, you essentially get a square root in the contraction factor. These are all upper bounds. Now I'm going to go to the second part of the talk, which is local differential privacy.
And which of those do you have corresponding lower bounds for?
That's the third part. I don't want to spoil the surprise. But so I'm going to talk about local differential privacy. For those of you that are familiar with differential privacy, essentially DP asks that the algorithm that you run, the output of the referee, doesn't give too much information in a distributional sense about any particular input. Local differential privacy is a strengthening of that, and it's essentially you don't even want to leak that information to the centralized referee. So Batman doesn't want the algorithm to know he's actually Bruce Wayne. So if I spoil that for you, but so that's essentially what local differential privacy is. In our setting, well, we've got a set of channels, that's kind of a tautology, but that are the channels that map to an arbitrary message domain, and these channels must preserve row differential privacy. For those who are keen on differential privacy, sorry, I renamed epsilon to row, so epsilon was already taken. And that actually requires that on any two different inputs, points received by any user, for the probability of any message under these two different inputs is within a factor, essentially 1 plus rho, e to the rho. So that's the family of channels we're dealing with. And again, they're randomized. And now the difference, one striking difference is they can send arbitrary length of a message if they want. But they do have to not reveal too much about their input in that according to that definition. So in that work with Jayadev, Himanshu, and Cody, we first give private coin upper bounds. So for those who know what wrapper is, it's a mechanism by Google, and another one is Adama response. That's a bit more recent. And we give two protocols that essentially take the output of these mechanisms and apply some post-processing to do the testing. Learning was already known by previous work. And we also give a public coin upper bound, which we call Raptor, for whatever reason, which essentially uses the previous contraction theorem with L is equal to 1. So put differently, all the players will use their public randomness to just divide the domain in two, so that when they just project their sample, their independent sample on that, they get 1 bit each to send. And if there is one thing we know how to do privately, is to send 1 bit. Essentially, you can use pretty much any optimal mechanism for that. You re-randomized. It's randomized response. And well, that gives the following interpretation, which looks very similar to a previous slide. You use public randomness to randomly map the domain into a smaller domain, which gives the best trade-off between your constraints and the distance shrinkage of the thing. And this is also something that looks a little bit familiar. So again, this is what you paid before in the centralized setting, and this is the extra factor. Again, for learning, public-private randomness doesn't help, at least in these upper bounds. But for testing, you again get a square root reduction. This time it only affects the k, but you get a square root reduction in private and public. So all I've given so far was upper bounds, which brings us to the third part, lower bounds. So this is the latest work I'm going to talk about. It's with Jayadev and Himanshu. And hopefully after that, why I call that the minimally contracting hashing will make sense. So this is essentially what the outcome is. Every upper bound I've given so far is optimal, up to constant factors. And as a corollary, which should not surprise any teacher here, I guess, sharing helps a lot for testing, but not really for learning. And in particular, we get a separation between testing uniformity in the public and private coin case. So, if there is no question, I'm going to go about how to prove these things.
Question, I guess. This is all for just one round.
Yeah, all that is. So we think all these results, if you're willing to blow up the notation, will extend to some tree protocol where the first player sends that and the second player sees the outcome of the first player plus its own, etc., but not in the full adaptive setting with several rounds.
The sequential settings.
Yeah.
Okay.
So how do we prove such a lower bound? Well, to prove a lower bound against testing, there is that construction that was due to Paninsky to prove the centralized bound, which is essentially what is the hardest case to prove to test uniformity. It's something that looks very close to uniform. So here's the formal definition, but with a picture, it's just assume without loss of generality that your k elements, k is even. You pair them in buckets of size 2. And then for each of the k over 2 different buckets, it's either going to be 1 plus epsilon over k, 1 minus epsilon over k, or the other one. So you've got k over 2 coin flips independent, and you just have that small perturbation. So that gives a family of 2 to the k over 2 different distributions. They are all epsilon far from uniform. And we want to say that it's hard to distinguish samples from the uniform distribution and samples that are drawn for one of these picked at random. At least that's what you want to do in the centralized case. Now we've got that extra thing that you don't want to look at the output, like the samples. You want to look at the samples after going through the channels, which is the main difference. So you've got an extra layer of abstraction there. And to do that, we would like to upper bound the distance, the total variation distance between what is the distribution of these n messages when the input is actually the uniform distribution, and the distribution of these n messages when the input is not the average of the distribution of these n messages under the odd instance, but the distribution of these n messages under the average odd instance, which is the main thing that allows you to prove the tight bound in the centralized setting. Put differently, one main issue is if you want to do that, the distribution of the n messages under the average odd instance is no longer a product distribution. You don't have that nice product structures of you've got n different things, and so it's an n product distribution. So it becomes hard to actually bound this thing directly. But if you want to do so, the right proxy to use is the chi-square distance. So again, you want to bound the TV distance between the transcripts in the 2 cases, yes and no case. So you can start by saying that the L1 distance square is upper bounded by the chi-square distance. And we want to show that this is much less than 1 because that means it's impossible to distinguish given these n samples, these n messages. And here the notation is YUN is the distribution of the n messages when the input distribution is the uniform distribution U. And PZ is the odd instance when Z is the vector of k over 2 bits that defines that instance. So if you go through that, you're going to end up, for every channel W, you will associate a positive semi-definite matrix, H of W, that's of dimensions k over 2 times k over 2, where the I1, I2 entry is defined that way. After a little bit of work, what you're going to end up doing is characterizing the contraction, the distance contraction after passing that through the channels in terms of 2 norms of this matrix, namely the Frobenius and the trace norm of this matrix. And that's reminiscent of the framework of SQ lower bounds via chi-square contractions, especially given the fact I've been talking about local differential privacy, and there is a relation between what you can learn in the SQ model and what you can learn in the locally differentially private model. However, here we actually get a different characterization in terms of different norms that are tighter, namely the trace and the Frobenius norm versus the spectral norms. So if you're familiar with these works, essentially if you try to apply that directly, you will get much weaker bonds than what we get. And also what I said before leads...
Is it a non-adaptive SQ, or the connection between local and SQ is for non-adaptive queries, right?
Yeah, it's one round, yeah. So what I said just does work and give the right bound for public coin protocols, but it would give the same bound for private coin protocols because I just defined one bad instance of distributions, and we want a higher lower bound, which this is not going to give. So we need a better perturbation than the Panitsky perturbation to get optimal, and so we can generalize the previous thing where like the perturbation we want to come up with some perturbation over -1,1 over k over 2, such that the bad instance is going to be defined that way. And essentially, if you take Z to just be a sequence of independent +1 -1 uniform, you will get back the previous construction. But now we get to pick that construction. That's the wrong arrow. Essentially, before we had one perturbation that worked against all possible public coin protocols because the public coin protocol is a convex combination of protocols. Now we want to actually, given some particular private coin protocol, we want to design some perturbation that's going to defeat it, fool it. And so we're going to try and choose that perturbation Z to do that by looking at what the collection of n-channel does, n-channels do, does, it's a collection, and try to hide the distance in the directions which give the least information possible to the referee, according to that. So essentially, you can look at the eigenvalues of that matrix, HW I've talked about, and try to hide the perturbation in like the eigenvectors direction that correspond to the smallest eigenvalues. It's essentially what we are doing here. And that's at a more high-level view. We get a max-min type of bound instead of a min-max. And if you didn't really care or missed that, it's essentially the upshot is we give lower bounds for learning, testing with public or private coins, and all of that depends on these two quantities, which are the Frobenius norm of the corresponding matrix, the maximum of all allowed channels, and the trace norm of this matrix. And bounding these things actually gives the lower bounds I claimed. I know you're going to have to trust me on that, but bounding these two things for the locally private setting and also for the communication start settings takes in each case 5 lines. And which that gives is this magnificent table. If you don't want to kill your eyes, also I'm going to put my slides online, but these are exactly the same thing as the upper bounds I gave before, except that now they are lower bounds. And this is the general statement, which is for a general family of channels, this is what we get. Now, the last part, the conclusion. So, what exactly happened there? Well, we looked at how pairwise distances between distributions contract when you pass them through the channels belonging to that green W. And well, pairwise distance will contract. And contract in which measure? Like the right one we argue is chi-square divergence. Finally, here's the definition of what that is. But what we do is we give a quantitative characterization of that contraction and also matching protocols that achieve it. And that actually leads to a very general view. If you want to find optimal algorithms against some kind of information constraint, well, you should look at this thing and design schemes that minimize that contraction. So, as a conclusion, we give a general framework for inference problems with local constraints over discrete distributions, which capture as special cases the communication-starved and the locally private regimes, and give optimal bounds for those. This is the first work we were aware of on distributed testing, except for I still can't pronounce it, but the work from '93 that considers simple hypothesis testing. And we give optimal protocols for the public coin and private coin uniformity testing in all the settings we considered. Of course, there are many directions and questions to explore. One of them, well, what if each person gets 2 samples, for example, or like many? I can say if each person gets infinitely many samples, it becomes pretty easy. You just have 1 bit to send. But what happens in between? Our lower bound framework doesn't apply as it is. And the upper bounds actually show that it's not a mystery why. Another interesting direction would be what happens in the continuous case, and in particular for the general parametric setting. So we've got some preliminary results when you want to test whether the mean of a Gaussian is 0 or big. It's as a big norm under these kind of constraints. And that's pretty much all. So thank you. Also, this is also not by me. This is by somebody named Damili.
Another question? Let's speak again.